Okay, hi, good evening, everyone. So let us quickly start with the class which we have finished till now. So we were through the heat transfer in various processes, right? So let us quickly solve few questions based on that area and then we'll proceed. Okay. So let us try to solve few questions based on this area. Yeah. So let us read this question. It says that there's a series of operations which takes place in a certain order and restore the initial conditions at the end is known as. So I told you sometime that whenever you have started any process, right? And when your final position is same as the initial, let us say you started from this one and then you reach back to this point again, then what do we say this that it has gone through a cycle. But I never said that only reversible process can happen through a cycle. It can happen that you were going through a series of process and then you return back to the original process, but you were going through irreversible process as well meanwhile. So what happens, let us say that you started some operation and let us say that from this process to this process you were, let us say that some irreversible process were occurring, let us say the reversible process something like this and then this one. But still what you can see is that you started from one, and even though there is some irreversible process, but still you manage to reach back to one again. This is 1 2 3 4. Then what is the meaning of cycle is that you started from one and you reach back to the one. Here also you started from one and reach back to one. That means it is nothing but a cycle only, right? This is nothing but a cycle only. So we cannot say that this it can be only reversible or irreversible. Why? Because most of us will get confused that this is about reversible cycle, but no, any thermodynamic cycle is called what? That it is a series of operation which takes place in a certain order and restore the initial conditions, right? Sometimes questions in the form of like basic definitions also appear in the exam. Okay, let us move to the next question. The next question says that it has given you few properties and it asks you to identify which among the following is an intensive property, which among the following are intensive properties. So let us quickly identify intensive property. First thing you need to recall from your memory is that intensive is the one in which there is no mass dependency, right? That the properties are independent of the mass. And how did we identify it? What we will do, that we will consider a system and we will part it into two, and then we'll look after the given what properties in the question, and then we'll find out. Let us see that temperature. So temperature, we have seen that even though the body is what cut into two halves, but I will never see that the temperature will decrease. So temperature is an intensive property. What about viscosity? Again, viscosity, for example, let us say that there is a container of oil, you divide it into two parts. This will never happen that the viscosity of this one and this one will get changed. It will always remain same, so it is also independent of mass. And the third one is specific entropy. Very important. Specific entropy. So again, see, if there was only entropy, then it will be extensive property. But specific word is mentioned here clearly. That means we have understood that specific properties are nothing but intensive properties. So this one becomes also intensive only. And what about thermal conductivity? Thermal conductivity is also not dependent upon the mass. Otherwise, what will happen? That let us say that you are using a brick wall, and based on its mass, this will never happen that the its thermal conductivity will get changed. Getting the idea? So thermal conductivity will also remain same only. So that means the answer becomes 1 2 3 and 4. The answer to the previous one was thermodynamic cycle. I have already taken. So thermodynamic cycle. Okay. Let us move to the next question. Let us read this first. See, What should be the attempt while solving any question in general, like in any subject or anywhere? You first read the question and try to recall the data, and then you will automatically follow. So what is given to you in the question, that in an open system and there are options listed. Let us read them one by one. It says that it's an open system is a specified region where transfers of energy and mass takes place. Okay, so this seems something which we have studied. So the option A automatically becomes the answer. But let us read the other options also. It says that this is a region of constant mass and only energy is allowed to cross the boundary. So this is talking about whom? This is talking about closed system, right? We have seen that in the closed system, what happened, that there was a reason. Let us say that we took the example of piston cylinder assembly without walls. Then what we were able to see is that the mass was anyway fixed. The mass was fixed, but the energy can what cross the boundaries. Like let us say that if you are heating this, then the energy can always cross the boundary. So this is okay. The third one, cannot transfer either energy or mass. So this is talking about whom? This is talking about isolated system. See, the questions from thermodynamics are always very basic one, but only thing is you need to mind the words. Here only the words game they are using amongst means against us. Okay, and the option 4 has an enthalpy transfer across its boundary and the mass within the system is not necessarily constant. So it says that the mass is not necessarily constant. This is true, but it is very specific. Like it says only enthalpy transfer across its boundaries. So this is not true. This is true, but partially true. Why? Because this is talking about only certain thing, right? But here your all the things are generalized. See, so even though D was correct, but D was not fully correct, the better option was A. So sometimes you will face this kind of situation. This is the case of what? A generalized case is this one, and this is one special case of this one. Okay. Let us read the what? Next question. It says that heat and work are nothing to be worried, that intensive property, extensive property. No, it's not extensive or intensive property. This is path function. Now we studied heat and work are not properties. So these two are automatically wrong. Na? Then only thing left is point function and path function. And we know something about point function. Point function, we studied that energies are point function. So energy is point function, but we studied that heat and work are path function. Why? Because if you are reaching from this point to this point, and if this is an PV curve, then we knew that this is the area which shows the work done. And if I am changing the path, so this differential area which I am able to see, this is causing the difference. So that is why heat and work are path functions. Okay. Let us read the next question. It says that the law which provides the basis of temperature measurement. We see that when we were discussing zeroth law of thermodynamics, yes, very good. This is zeroth law of thermodynamics. When we were into zeroth law of thermodynamics, then the concept of thermometer was introduced. So the zeroth law of thermodynamics become the option. Why? Because zeroth law of thermodynamics was the one who told us the relationship between what? So let us say that this was A, this was C, and this was B. Then if TA is equal to TC and TB is equal to TC, then TA is equal to TB. So here we knew that this TC is acting as thermometer, and here the basic of temperature measurement came into picture. Yeah. Let us read the next question. It says that thermodynamic work is the product of. We have seen that thermodynamic word. See, here they have clearly mentioned thermodynamic work. So we have seen thermodynamic work something like this, integral of PdV. So let us talk about what are these properties. One thing is pressure. and another thing is volume. So what happens in pressure and volume? Pressure is nothing but an intensive property. Can you see that when we were dividing the chamber, then we will never be able to finding out the pressure will get changed. Why? Because the pressure is not dependent upon the mass, right? So pressure is in what? Intensive property. Okay. So this is one. And what about volume? Volume is obviously an extensive property. Thing to be worried. Okay. And what is the relationship? Yeah. An intensive property, right? Like pressure is an intensive property and change in an extensive property, right? So this becomes the option pressure intensive property and dV is an change in extensive property, right? Next question. It says that the, let us read the question carefully. The gauge pressure in a truck tire before and after the journey was recorded as 200 kilopascal and 220 kilopascal respectively at a location where atmospheric pressure and temperature was 100 kilopascal and 27 degrees Celsius respectively. Then it says you how much the rise in temperature of tire air after the trip. So let us read this carefully. See, we have seen the examples of like applying the ideal gas equation to certain scenarios. Okay, so sometimes they will leave some hint for you and they will expect you to solve the question, right? So let us try to solve this one. Okay, so it says that the gauge pressure. So one thing before we solving this question, like we have seen this equation PV is equal to MRT, right? Then what the P which we are using into this one now, this is absolute pressure. This is never gauge pressure. Okay. So we'll always use absolute pressure data here. Okay. So absolute pressure we will be using here. That is why they have mentioned gauge pressure and atmospheric pressure. What? Individually. And this gauge pressure is, or we can write absolute pressure is gauge pressure plus atmospheric pressure is nothing but P absolute. So now coming back to the question, it says that the gauge pressure in a truck tire before and after the journey. See, somebody was on a journey and he found that initially the pressure was 200 kilopascal, and later on he found out that the pressure has changed somewhere to 220 kilopascal. And it also says that to a location where atmospheric pressure and temperature was 100 kilopascal and 27 degrees Celsius respectively. Then see, what I will assume that initially they have not mentioned any temperature, like the initial pressure is given but initial temperature is not given, but we have to solve this one. So what I will do is that I will assume the initial temperature as the room temperature only, like let us say that initial the temperature was 27 degrees Celsius, and the second thing is that pressure is also given. So P1 becomes what? Gauge pressure plus atmospheric. So gauge pressure is given to you, right? Yeah, gauge pressure is given na the 200 and 220. So I am making the notations one before the journey and two for after the journey. So 200 plus P atmospheric is mentioned 100. So P1 is 200, the gauge pressure plus atmospheric pressure is given as 100. So this becomes 300 kilopascal. Okay. And then volume one. What about volume one? This is not mentioned. And let us, this is before journey. Okay. And then after journey. What happens after journey? The temperature they are willing to ask us. Pressure is given to us as, what is the absolute pressure now? 220 plus of 100. So this becomes 320 kilopascal, right? So P2 is also given to us and P1 is given to us. T1 is given to us and we have no idea about T2 and V2. So in this case, what we will assume that even though the tire's volume will try to change itself by bit, but we will assume that here it has undergone constant volume process. So what I will assume that V1 is equal to V2. Then now how if you apply the ideal gas equation that PB is equal to MRT. So then for constant volume process, it will be sorted as P1 upon T1 is equal to P2 upon T2, right? So P1 is given to us as 300, T1 is given to us as, and see, here you will always use Kelvin temperature, absolute temperature, okay? So the temperature T1, this also becomes 300 Kelvin only. You will add 273 into it. So this becomes 300 Kelvin. And what about P2? P2 is given to us as 320 and then they are deciding it as T2. So the T2 becomes 320. Then in degrees Celsius, this will become 320 minus 273. So this is nothing but 47 degrees Celsius. So this option is correct. Okay. See, sometimes they are mentioning these kind of option like insufficient data. So most of the time we should abstain ourselves marking this option. Like even somebody might have used this option, but it will lead ultimately to wrong option. Why? Because if using certain assumptions you are able to reach the solution, then we should try to possibly reach the solution. Okay. CV I have nowhere used the. So where I have used CV. I have never used CV. Please tell me. Yeah, like constant volume process, but there was no need. Why? Because when we will use this Q is mcv dt, right? Like then if I had the data that what is the heat loss, if I had the data of heat loss, then I could have used that. Okay, I know the mass, then I know the dt, like dt was here to determine, then cv other things. See, like yeah, your concern is fine that if it's a constant volume process, then q is mcv dt, absolutely true. But you need to identify one thing now, that where you will find out other data. Like even though you are writing this equation, then what about q, where you will find out q if it is not mentioned in question. Same when you are, where you will find out m, where you will find out cb. Like okay, cv is the standard value you can remember, but right. Yeah, like whenever there is like sufficient data, then we could have used that. Like let us say that somewhere you were solving the question and they told you that that heat loss was something like heat loss value they will mention, right? Then they will ask you that what was gt, then you can find out. We'll see if possible certain kind of questions based on this area also. Okay, let us move to the next question. It says you that the condition for the reversibility of a cycle is. So what things were we were taking care so that we will lead ultimately to the reversibility of cycle. So let us read the options one by one. It says that the pressure and temperature of the working substance must not differ appreciably from those of the surrounding at any stage in the process. Yeah, we have seen this one. Why? Because I told you that if there is certain difference between you and your surrounding, then you must be losing some heat to it. That means you are interacting with the surrounding. If your interaction with surrounding is what? Appreciable, If your surrounding with the interaction is appreciable, then you cannot say that your process will be reversible. Why? Because like, so let us say that you are giving some heat to the surrounding, but the same amount of surrounding will not lead to same type of delta T. Let us say that you were at 10 degrees Celsius and you lost some heat and you reached to 3 degrees Celsius. So here you have lost certain Q, but this will not necessarily guarantee that enough that Q will help you to get that delta T. Why? Because here your Q was, let us say that you must have supplied some heat, right? So this heat which you have supplied, this must have taken care of certain other things also. So this is never possible to reverse if you have interaction with the surrounding. So this is the correct option. This we have seen only, just what recapitulation. Okay, next, all the process taking place in the cycle of operation must be extremely slow. We have seen this one also, right? Like if you are not slow, then you are not in equilibrium, and if you are not in equilibrium, then what, this process cannot go reversibly. Then the third one is the working parts of the engine must be friction free. Working parts of the engine, we have talked about it, right? Like if the parts are not friction free, then you are losing certain energy into friction, and then again that same amount of energy if you are getting back, then this is not possible that your system will get back to the initial condition again. So in that case also, the this will lead to what, irreversibility. So the working parts of the engine must be friction free. So in that case I can see that A, B, C all are true, and the fourth one is given as all of the above. So this one is the correct option. See, sometimes what happens that we should look after that if they have anywhere given all of the above option, like all of the above and when none of the above, so we should be precautious, right? Like, see, in, like, see, somebody was solving the question and he thought that okay, I have found the correct option and he has marked option A, but indirectly he is telling that B and C are not correct. Why? Because there was one option who was telling that all of the above are true. So we should be careful whenever we are solving questions and they have given an option as all of the above or none of the above. Okay, let us read next question. It says that the internal energy of an ideal gas is function of. So we have appreciated this fact that internal energy of the gas was function of temperature only, right? When we were solving the heat transfer value for various process, then we have appreciated this fact that the even though we know the temperature only, we can find out the internal energy of what, ideal gas. So mind these words and then we will tell them what, that absolute temperature only. See here they have specifically mentioned absolute word. Absolute temperature means what, in always Kelvin scale. Okay, let us read the next question. It says that in reference to thermodynamic equilibrium, it is required to have, it is required to have, yeah, very good. This is required to have mechanical, chemical, and thermal equilibrium. So the next best option is all of the above. We have seen these things. I am trying to help you that whatever we have done in the class now, that these are all questions appeared in some of the PSU exams or state engineering services. So I have picked these questions from there only. So you will appreciate that the questions are what, coming from the areas which we have studied in the class. Okay, it says that if value of n is zero in the equation pb to the power n is equal to constant, then the process is called. So what you will do, that you will do nothing, you will do this exercise and you are done. So n is 0, that means v1 to the power 0 is 1. And what about p2 into v2 to to the power n is equal to 0. So this again becomes 1. That means P1 is equal to P2. So can I say that this is a constant pressure process? So where we can see the option constant pressure process. See, whenever you are facing any question, now you try to break the questions from what in like in given form to the forms which you have seen. If you will be able to break the given data now, then you will automatically lead to the correct answer, right? So what I did, that I know that okay, that how did we recognize the process, like looking at the pressure, temperature and volume things, right? Like when pressure was constant, then only I recognize that okay, it's a constant pressure. Even then volume is constant, constant volume, temperature is constant, constant temperature, and like that. So looking upon these data, we identified the nature of process. So how we are doing that we are applying the given equation to instant, and then we will find out. So every time what you will do, that you will apply the given equation at two time instants. That is it. Okay, let us read the question. It says that which of the following is correct statement for energy? For correct statement for energy, let us read all of them one by one. Okay, first option says that energy is not the property of the system. But if you remember, we appreciated this fact that q when q was in the first law, we have seen now that dq was delta u plus dw. Then the difference between dq minus dw is delta u. Okay, so this is also true that difference between two path functions is always point function. So delta u is energy anyway, so then it becomes what? It becomes point function. Why? Because this is the difference of two path functions. So this is the point function, and point functions are properties. So if it is says that energy is not the property of the system, then it says the wrong statement. Why? Because energy is point function, and point functions, we have seen that point functions were properties. Okay, energy is path functions. This we have seen that this is not true. Then it says that the change in energy between two states of a system is different for different path followed. Wrong. Why? Because I told you that, let us say you are reaching from 1 to 2, then if energy is a point function, then it will never mind that if you have reached through which path. Like there are various paths which you can take from reaching from this point to this point, but you will never see that this is path dependent. So I can again say that energy, since it's a what point function, then this option is also wrong. This option is also wrong. This is also wrong. So D option, this is only left, and this is true. And this, however, we have seen many times. I have told you now that if you are started from this one, yeah, initial and final states are same in cyclic integral. Whenever they are mentioning you cyclic integral, that means you have they will be asking you that what happens throughout the cycle. And we have seen now that in cyclic integral of dq was cyclic integral of dw. Have we seen that this in first law for a cycle, right? We have seen. Then what we will do, that delta eu energy is the difference between these two. So let us try to find out the difference, and we know that this is equal to this one, so this anyway became 0. So what I can say, that the cyclic integral of d is 0. See how we have break the given information to reach the required, even though the option elimination might have also worked, but conceptually we understood that since dq is dw, then dq is dw, and delta u we see from the first law that this is the difference between these two. So this anyway have to become 0. Okay, let us go to the next question. Let us read all of us read this question first, and then we will solve. What is given to us in the question, please, everyone? It says that a piston cylinder arrangement has air at 600 kilopascal, 290 Kelvin, and volume of 0.01 meter cube. Okay, so many data. And it says that during a constant pressure process, if it gives 54 kilojoule of work, the final volume must be. See, then what we will do, that we will look after, yeah, very good. So what we will do, we will look after the given data and the required data. So given data is pressure, and anyway this is constant, and temperature, initial temperature is 290 Kelvin, and it has also given V1 as 0.01 meter cube, and then it has mentioned the constant pressure work, and work done is 54 kilojoule. Okay, then it says the what is the final volume. So where, see, if we have given data about work, then where we have seen the all these things related like pressure, volume and other things. So what I will do, that yes, I have seen this one, W is integral pdv, where we have seen these data related, and v2 is asked to us. So what I will do now is that W is given us as 54 is equal to pressure is given to us, yeah, 600 and kilopascal. See, we should always try to track these data also, like kilopascal and kilojoule. So then we need not to convert the units also, otherwise we will have to work upon that area also. Okay, and since it's a constant process, P into V2 minus V1, V2 is asked to us and V1 is given as 0.01. So let us solve this one and we will get. So can you tell me what is the answer, please? Please solve this one quickly. Okay, so this is 54 divided by 600. So this is nothing but 6 nines and this is 600, right? So this is 0.09, right? Is equal to V2 minus 0.01. So this becomes V2 0.09 plus 0.01. So this is becoming 0.10. Okay. So the A option is correct. Okay. I hope all of us are getting right. Let us solve the next question. It says that the work done during an isothermal process is. What do we know about isothermal process? In isothermal process, the temperature remains constant. Isothermal means temperature is constant. So, okay, yeah. So integral PdV, then P, we appreciated that we wrote in form of C upon V dV. So this was C into ln V2 upon V1. And we will have to be careful about this data. This was either of P1 V1 or P2 V2, right? And let us look up the options. Is it, yeah, option A is correct. P1 V2, no, wrong. P2 V2, okay, we need to check. This one, no, wrong. And what about P2 V2? See, if P2 V2 is given, then log of P2 upon P1. Is this data correct? Why? Because PV is equal to constant. That means P1 V1 is equal to P2 V2. Then V2 upon V1 we are getting inside this one, right? Like we are integrating this one now. So can we replace V2 upon V1 by P1 upon P2? Right, see, be very careful. V2 upon V1 can be written as P1 upon P2, but here they have mentioned in the form of P2 upon P1. That is why it is wrong. Like if they might have used the negative sign here, then we can say that okay, this is true. But since they have not even used the negative sign, then this option is correct, this one is wrong. Okay, yeah, Like somebody, if they have remembered in terms of pressure, then they will mark this option also correct. But like even let us say that most of the us are used to want like whatever we feel is correct, then we don't even check the other options also. So if they have given the data in this form, then they must have used minus, or they could have used the correct explanation. Okay, next question. It says that which thermometer is independent of the material of construction? Tell me which one. Ideal gas, right? Ideal gas thermometer. I told you now that how it became ideal gas thermometer. Why not others? Why? Because we have seen that in ideal gas thermometers, we reach to what? Let us say that if the thermometric property were reducing to what, like let us say that this was the form like P1 upon T1 is P2 upon T2 for constant volume. So is there any material property involved in this one? No, right? Even if you use let us say oxygen, even if you use nitrogen, if you use helium, neon, argon, whatever is you are willing to use, like all of them, there is no property used here. But when you will be using, let us say that resistance thermometer, then R is R naught plus alpha T, let us say this is the relation, then this is very specific, this relation is very specific for any material. Like this relation might get changed depending upon the nature of the material, and you can see some slight variation in the temperature, but we can see that this is independent of the material of the construction, right? Next question. This is good one. Let us try to read the question first and then we will solve this one. What is given to us is that they are willing to ask us that what is the efficiency of this hypothetical cycle. See, efficiency, I have not talked about it, but efficiency is that what is the work you are able to get, like work output divided by what was the input you were supplied, and input mostly we are supplying in terms of heat input. So that is why I am writing this specifically in terms of heat and work, that what was your work output and what was your heat input. The ratio of this one will tell you the efficiency. Now it asks you that what is the thermal efficiency of hypothetical cycle. Okay. So this has given you a TS cycle, right? So in TS cycle, what happens is, I'm sorry. See, in TS cycle, we'll appreciate this one later, that in TS cycle, we are getting this one as work like heat. Like the way we have seen that W is integral PdV. Na? Similarly, that Q is integral of TdS. Okay, so the area of curve on the s-axis, like on entropy axis, will give you what? Heat interaction, and work output itself, we can write that this is the difference between Q input minus Q output upon Q input. Okay, so, or one more thing, that the area enclosed will give you what? The work interaction. So this is anyway giving you the work interaction, and area of this triangle will be what? Half of this base, and the base is here what? 5 minus 1, 4. So can I write down this is 4 into what is the distance? This distance is 700 minus 300, 400, right? So this is giving you the work done total. Okay. So this is 800. So I have written done the work value. Why? Because the area enclosed by the curve on TS, either on TS or PV, will give you the work interaction by that cycle. So work interaction I know now. And what about heat interaction? So see, this is the work interaction, but cycle can we see that this is the amount of heat which is rejected. Okay, so we'll have to take care of this Q also. Okay, and what is that Q input? This area which you are counting in work plus this one. So this already I know that this is 800, and plus this area is 4 into what is this axis? 300. So 4 into 300. So this is what? 2000. So what will be the efficiency? This is the work output. Work output is 800 and work input is 200, 2000. So can I write down this one as, can you tell me which option? C. This is 0.4 now, right? So 8 upon 20, 80, 0.4. Okay. Got this question? Means what I was trying to help you know is that one thing is that area enclosed will give you the work, but the total area, like from this one, like on the axis, this is giving you the total heat interaction. So indirectly we have used this concept that cyclic integral of Q is cyclic integral of W. So if we don't know about delta W, then what I will do, that I will find out delta Q. So this is nothing but delta Q. Here this is the amount of heat which was supplied, and this is the amount of heat which is rejected. Okay. Next question. It says that the characteristic gas equation of gas is PV is equal to N R bar T. PV is equal to N bar R bar T holds good for whom? Option A, monoatomic gases. Option B, diatomic gases. Option C, real gases. Option D, ideal gases. See, even though we know that this is ideal gas, right? And this is correct option, but they have mentioned cleverly, like they have mentioned monoatomic, diatomic, real gases, so that you will get confused that which gas we were using this equation. So you should always mind that this equation was valid for whom? Ideal gas. Okay, next question. It says that a perfect gas at 27 degrees Celsius is heated at constant pressure so as to triple its volume. The final temperature of the gas will be. So again, let us use the subscript 1 for initial and 2 for final. So it says that initial temperature is 27 degrees Celsius at constant pressure. So P1 if it has some value, and V1 it has some value. Okay. Then it says that T2, this we need to determine, and this is given as that P2 is P1. Why? Because it's a constant pressure. And what about volume? It says that the final volume is triple, like triple its volume. So V2 is 3V1. So can I apply this P1 V1 upon T1 is P2 V2 upon T2 for constant pressure process. So can I directly remove these parts P1 and P2, and then we will use the relations given to us. V1 upon T1 I know 27 degrees Celsius, but we will always use what? In Kelvin scale. So this will become 300 is equal to V2. V2 is nothing but 3V1 upon T2. So what is T2 now? V1 and V1 got cancelled. So T2 becomes 3 into 300. So this is nothing but 900 Kelvin. Mind the word, the temperature which you are getting here is 900 Kelvin. But what about the options? What about the options? They have given 900 degrees Celsius. So 900 degrees Celsius 900 degrees Celsius. See what happens now, that whenever you are solved, like you see that you are getting the magnitude of 900, you will not match the units. You will not match the units. You will directly look after that where you can see 900 and you will tick this option. But this is wrong one. Why? Because the temperature you obtained is in Kelvin scale, but options given are in what? Degree Celsius. So you will convert them into degree Celsius. So what you will do, you will subtract 273 from this one. Then this is nothing but 627 degrees Celsius. So 627 degrees Celsius. So this is the correct option. Okay. Then it says next question, that heat transfer to a closed stationary system at constant volume is equal to. So we have seen that heat transfer to the closed stationary system, mind the word closed stationary system, at constant volume. They are talking about what? Constant volume. So we have seen that Q was du plus delta W, we have seen, right? So this is for constant volume, and mind the word closed system, then only I can write down this one as 0. If there was no closed system, I could not have used this one. Why? Because this was defined for whom? Closed system. And if it is a constant volume, dV is 0, so this is directly 0. So delta Q is equal to du, and then option is ready, na? Then they are asking about delta Q. So heat transfer to a closed system at constant volume is nothing but change in internal energy or increase in internal energy. So this is the correct option. Okay, let us solve this question. This is very good question. Let us solve this one. It says that a system absorbs 100 kilojoule of heat and does 60 kilojoule of work along the path 1 to 3. Let us first look after where is path 1 to 3 located. So they are talking about this path. Let me highlight this one. This is 1 to 2, 2 to 3, and 3 to 1. They are talking about this path. So 1 to 2, 2 to 3, they are asking you that system absorbs means what? The heat is supplied. So heat supply is treated with positive sign. Please look after how I'm solving. And then it says that and does 60 kilojoule of work. That means it is supplying the work. That means this is also in positive value. Okay. Then can we find out the delta U between 1 to 3? Why? Because you are using 1 to 2, 2 to 3, and 3 to 1. So can you say that the delta U in this whole cycle, what is delta U here, is 100 minus 60. See, let us not complicate this one. We will see that there's an interesting phenomenon in this one. Let us look after this question again. It says that the same system does 20 kilojoule of work along the path 143. It says that when you are using the path, let me change the color. It says that when you are using the path 1 to 4, 4 to 3, then it says that the system does 20 kilojoule of work. Then it says the heat absorbed during the path 143 is. Then they are asking you that what is the heat absorbed during the path 1 to 4 and 3. So how you will solve this question? Tell me. Tell me how you are going to attempt this question. See, what I will do is that I know delta Q 1, 2, 3. So for process 1, 2, 3, see, if I know U3 minus U1, then I can solve this question also. Why? Because 1, 4, 3. So if I know the difference between U, then I can apply the 143. For 143, what is given to you is that the same system does 20 kilojoule of work. So Q becomes plus 20 kilojoule, okay? So what is delta U here? 1, 2, 3. Let me erase all the ink first. See, now let me help you to understand in better manner. This is 1, 2, 3. Yeah, internal energy change will be same, but the sign we need to look after that. What about the sign? So when you are applying between 1 to 2, 2 to 3, so can I write down that this is plus 100 is equal to delta U. So your final state is 3, right? So you will write down U3 minus U1, final minus U1 initial, plus W is given as 60, so this is 60. So what is the value of U3 minus U1 here? This is 100 minus 60 is equal to 40. Let us go to 1, 4 and 3. So for 1, 4 and 3, what I will do, again I will apply the concepts of this first law of thermodynamics. So it says now Q, then Q, I don't know what is the Q. Q I will remain same. And the heat absorbed during the path 1, 4, 3. And the same system does 20 kilojoule of work. So same system does 20 kilojoule of work. This much I know. And what about the U3 minus U1? Again, here we will be using U3 minus U1. So U3 minus U1, why? Because you have started from 1 and reached 3. Here you have started from 1 and reached 3. So here U3 minus U1 is 40. So 40 plus 20 kilojoule, that means Q is 60. So out of this Q is equal to 60, 20 is done to you convert into work, and 40 is converted into internal energy. Okay. Discussion. It says that a mixture of gases expand from 0.03 meter cube to 0.06 meter cube at constant pressure of 1 megapascal and absorbs 84 kilojoule of heat during the process. The change in internal energy of the mixture is. So we have to read the question. Now let us try to solve this one. So it says that at constant pressure, mixture expands from 0.03 meter cube to 0.06 meter cube. So one data is this one, and it says something about heat absorb. Then it asks you what is the change in internal energy. So I will again, where we have seen the couple things of energy, work, and what heat. So we have seen this in first law of thermodynamics. So here you have been given that Q is plus 84. Why? Because mind the word absorbs. Okay. And what about W? W is PdV, integral PdV, but it has mentioned constant pressure. So what I will do, 1 megapascal. Here this is in kilojoule. So here what I will do is that I will convert it into kilopascal, and in 1 megapascal means 10 to the power 6. Like let us say that it says 10 megapascal, then what you will do, 10 into 10 to the power 6. This is the thing. Then in order to convert it into, this is Pascal, like 10 to the power 6 Pascal. Okay. So convert it into kilopascal, you will divide it by 1000, right? So constant megapascal. So 10 to the power 6 divided by 1000, it becomes 1000 kilopascal. And what is dV from 0.03 to 0.06? So V2 minus V1 we used to write. So 0.06 minus 0.06. 0.03. So this is 1000 into 0.03. So this is 30 what? Kilojoule. Then you will be able to reach the correct option. Then you can see here that delta U will be 84 minus 30, that is 54. So if you don't follow the sign convention, can you see that 84 plus 30 is also in the option? Can we see that? If we don't know that the difference between V2 minus V1, V1 minus V2, then we are bound to get the wrong option. And one more is important, that if we have not converted this unit, then see here we must be getting very small units, right? Like it must be something like 3, 4 and like that. Okay. See the all possible options are okay, 1000 pound, right? See what happens that in megapascal there is 10 to the power 6 Pascal, right? In kilopascal there is 10 to the power 3 Pascal. Okay, like let us say that I tell you that pressure is 70 megapascal, then what do I mean is that this is 70 into 10 to the power 6 pascals. Got the idea? Let us say that I say 58 megapascal, then it is 58 into 10 to the power 6 Pascal. So here they have mentioned you 1 megapascal, then it means that 1 into 10 to the power 6 Pascal. But I am willing to use what? What? Kilojoule. That means if I will be using kilopascal, then I will get kilojoule. So I know that in kilopascal there is 10 to the power 3 Pascal. So in order to convert it to kilopascals, what I would do is that I will divide it by 1000. Why? Because this is 10 to the power 6, this is 10 to the power 3, and I will get that 10 to the power 3 pascals. Clear? Next. It says that 1 kg liquid specific heat 3 kilojoule per kg Kelvin is stirred in a closed chamber and its temperature is raised by 10 degrees Celsius. Okay. And then it says that heat loss to the surrounding is 3 kilojoule. The work done on the water during the process. So again, whenever you can see the mixed data of heat, work and energy, you will first go to what? First law of thermodynamics. You will see that what things are given to you as per the first law of thermodynamics required data, and then you will apply it, right? So now let us first look after. It says that there is a closed chamber. Closed chamber means what? That its volume is not going to change. Okay. And in this closed chamber, this is not insulated. This is the sign of insulated. Since heat loss is given to you, you cannot say that this is insulated, right? And then it says that there's a stirrer and you are giving it some rotations, and there is some work what given by you to this system, right? Okay. Then it says that it's it this stirrer is raising its temperature by 10 degrees Celsius. So this is what, like we can see here the Q value. Q value is what? MCP dt. How I am writing this one? Because what is the heat interaction? Heat interaction is nothing but MCP dt. So here this is given to us as M is 1. So let me use 1, and CP is 3. So we'll use 3. And what about DT? DT, it says that the temperature is raised. That means T2 minus T1, T2 minus T1, then T2 is higher, then only this is raised. That means this is the positive value. So can I write down Q is 1 into 3 into 10? That means this is 30 kilojoule of work you are supplying, like not work, you heat, right? And then it says that heat loss to the surrounding is 3 kilojoule. Heat loss to the surrounding is 3 kilojoule. Then it says that the work done on water during the process. So what is the heat lost? Heat lost is minus 3, right? Q value, this is heat lost is minus 3 is equal to, and here this Q value which MCP dt we remember now, can we recall this from our, can we recall this from our that process where the chamber was constant, that means volume was constant, then can you recall that Q value was U? Can you recall? Yes. So here your U value is directly given by whom? Q, and Q we have determined this is 30. So is equal to what? Q is delta U and this is positive value plus W. So W will become what? Minus 3 minus 30 is equal to minus 33. So minus sign is not given to you. Why? Because they have already mentioned this word, the work done on the water. On the water means what? Upon the system. Upon the system. Upon the system. So if you are getting upon the system, that means minus 33. That means you automatically know this is upon the system. So your best option is 33. See, why I have first help you to determine this Q. Why? Because this is how we have used to see. Okay. Then I later appreciated, since this is an closed chamber, then this stirrer which you were using to steer is nothing but this is giving the work to each, which is raising its internal energy. So here what happens that this is the stirrer and this is giving you some what? No, the stirrer is also the part of function system only. So this stirrer is giving you work of 33 kilojoule, and 3 kilojoule of this one is lost to the surrounding and 30 kilojoule left with it. Okay, so this is, see, this delta U we have seen now, this Q is delta U. So can we see that out of the 33 which you supplied, which we have received here, the 30 is used to raise its temperature, and the out of those 3 is going into the surrounding. Okay, so this is all about like questions which you will be facing in the upcoming PSU exam. Like we have seen the how they will play with words, how they will play with the sign conventions even, and like that. Yeah. Okay, so this is all about till first law in closed system. Till now we have applied all these things to closed system. So now we will do an open system analysis. What we will do is open system analysis. Okay. So in open system we have seen few things. Let me write the keyword that what we are going to understand here is first law applied to whom? To open systems. So when you are applying first law to the open system, then you should know how we were used or we define what? Open system. So what happens in open system is there will be open system or control volume, right? We have seen this one earlier. So what will happen in the control volume or open system, that there will be one inlet through which the mass which you are going to study will come into picture, and there will be one outlet through which the mass will go out of the system, right? So this is the place where mass enters, and this is the place where mass will go outside. And let us say that you are at some respect to the data. Okay. So this is, let us say that elevation of some Z1, and this is at some elevation of Z2. Here, let us say that this is the entry point where I have following things, that I have some mass flow rate m dot, then I have some enthalpy here, that is h1, then I have some velocity here, and which velocity will contribute into kinetic energy, and then I have potential energy, we have counted it through Z1, and then what we can have, that we can have pressure and we can have specific volume here. Similarly, here we will have at the exit, this is the exit point, then here we will have again mass flow rate, we will have H2, we will have what, velocity, we will have pressure, we will have specific volume, and then Z we already know. Then when we apply it, this is your control volume. Okay. And here you are supplying some Q dot, and you are extracting out some W dot. Okay. Then when you will apply, see, this is nothing but we will be applying the first law to the open system. So what we have seen in first law, can we recall? We have seen this one. We have seen this one. But this is very generalized. This is very generalized. Rather than delta U, we have seen that the original equation was this one. But in order to simplify it for closed system where the potential and there is no flow, there is potential energy change which is very less, and no kinetic energy change, then we neglected those part, and then we said that this delta is equivalent to delta U. But this was like this one. So can you apply now this delta E to this delta U? Okay. So when you will apply this one now, then what is this delta E? This is nothing but E2 minus E1 always. Okay. So let us now apply this one. Then what will happen? Can you write that you are applying some heat Q1, and what I would do is that I will take this E1 part on directly on this one, and E2 plus W on the right hand side. Can I write down that dQ plus E1 is equal to E2 plus dW? I can write, right? So this is the concept of what? Steady flow energy equation. So can I write down now that Q dot plus the mass flow rate I am taking as common into, you have H1, you have V1 square by 2, and then you have G into Z1, which is helping you to find out the potential energy, right? So can we see that the left hand side, this dq upon E1 has been introduced here. And then this is equal to what? We have seen this is E2 plus dW. See why mass flow rate multiplication? Because most of the time you will be given with the specific properties. Like if what is kinetic energy, m dot into v1 square by 2. What is potential? M dot into gz1. So similarly, what you will do here, that m dot into, now these subscripts will change into h2 plus v2 square by 2 plus g into z2 plus what? W. And what is your W value? W value anyway is W dot, we know. So this is your steady flow energy equation which I have written here. So if I write this one as generalized term, like which we use to see is that Q dot plus m dot into h1 plus v1 square by 2 plus g into z1 is equal to w dot plus m dot into h2 plus v2 square by 2 plus g into z2. This is very important equation. But what are the mistakes which we will be doing here? Let us counter them one by one. First thing is that we mass should be taken care. Mass flow rate should be taken care. First thing, very important. Most of the time we are forgetting these units. And the unit of H1 is nothing but U1 plus P1 into V1. Let us try to understand what is this. H1 is U1 plus P1. See, let us come to this one. See, every time there is some fluid trying to enter into it and some fluid is trying to go out of it. That means at this point, let us say that if I consider a block of fluid, then what will happen if this is trying to enter into it? That means the fluid before it, like let us say that if I am talking at this point, then fluid before it must have tried to push it into this contrail volume. Yeah, H is enthalpy, but I am helping you to understand what is the physical meaning of this enthalpy and all. See, what happens that every time there is some differential mass coming into it and some differential mass going out of it, right? So what will happen that this mass will not automatically come into this control volume unless there is someone who has tried to push this differential mass. So this mass when gets some push, that means it has got some energy again, or what, some velocity even. So that velocity which it has gone now, so that is signifying you that okay, I have some flow energy, right? So this flow energy is quantified by whom? Pressure into volume. When you will take product of this one, so this is helping you to understand that okay, if I have come in, if I am flowing and then I am possessing this much energy with me, then every time when you are dealing with some flow, that means this pressure and its velocity will always be there and internal energy is always there. So you will be always dealing with what, the sum of these two. So that is why we take it in, take counter of this one in one single variable, that is called H, and the unit is kilojoule per kg. Most of the time they will mention you this one is in kilojoule. Why? Because if they will mention joule, the data will be they will show them by bigger numbers. So in order to shorten the number, what we will do, that we'll use a kilojoule. Then what happens here is, we know that the data is kilojoule, but what about m dot into v square by 2? This will give you the unit in joules, right? And this kg multiplied by m dot will help you to reach the unit kilojoule per second. But here the metric units are multiplied, so this way you will get joule. So in order to take care, what you will do is that to convert it into kilojoule, you will always divide it by 1000. Which part? This part and this part also. This will give you units in joule, but these data are mostly given into what, kilojoules. So what we will do, that we will be precautious that I have to divide it by 2000 and this one by 1000, again this one by 1000 and this one also by 1000. Then only you will reach to the correct answer. Otherwise you will find out that this magnitude of this one is getting out of your hand, means you will find out that this is very bigger data, but this should not be ideally. Okay. I hope all of us appreciate this fact. Okay, now, so what we will do, that we have various steady flow devices. So we will apply this steady flow energy equation. This equation which we have got here is steady flow energy equation. Okay. So now what I'm trying to do is, we'll apply this steady flow energy equation to various devices and we'll see how we can utilize this one. So first is nozzle. I am trying to apply this steady flow energy equation to a nozzle problem. So what happens in the steady flow energy equation is, let us write down the first, the generalized term. Always what we will do, that we will write down the generalized term. Okay. And then if there is something which can get cancelled out, we will cancel them. Okay. Can you see that this, let us first draw a nozzle. So in nozzle mostly they are insulated. Okay. And nozzles do not provide you any kind of work. So first thing is do that this is 0 and this is 0. Okay, one thing. And second thing, see, when you will be applying this steady flow energy equation, and then when you will try to find out that what is the this Z1 and Z2, then what you will see, that this difference will be not bigger. So what you will do, that this change you will write 0. See, if there is some problem and they will say mentioned about that the enters at 10 meter and exits as 5 meter, then you are free to use, right? Like if they are not mentioning you the data, then you can use certain approximation. Like if they will give you the data about every individual, like let us say that they mention you there is some heat loss, then you will take care. Okay. But if they have not mentioned, then what you will do, that these are standard terms, you will automatically assume that if it is not given, then it is 0 only. Okay. So now can you see that your equation has been reduced to m dot into h1 plus v1 square by 2000 is equal to m dot into h2 plus v2 square by 2000. So can you see that if you are not aware how to sort, means eliminate the unknowns, then you will be in difficult situation. Okay. Then can I see that the nozzles are used to increase the velocity of the fluid passing through it. So in general, if they will not mention you the velocity even, the entry velocity even, then if they are given, if they are providing you the data, you use them. And if they have not provided, what you will do, directly 0. So can I see now that this m dot and m dot will also get cancelled out? Then my v2 value means velocity at the outlet, what will be this value? Can I see that this is h2 minus, not h2, h1 minus h2, v2 I am trying to find out, square root of into what, 2000. Yeah, V2 is square root of, see if you are not getting, let me help you with one more step. Can I write down that H1 is equal to H2 plus V2 square by 2000. So can I write down that V2 square by 2000 is equal to H1 minus H2, then V2 square is square, this 2000 is multiplied into it. So H1 minus H2 into 2000. Yeah, next. So we can apply it to more devices, like we have applied it for nozzle, then we can apply it for, let us say, diffuser also. And in diffuser, the only difference is what we have seen in nozzle, the diffuser is the just reverse of it, that this is diffuser. Okay. Then what diffuser would do is that it decreases the velocity. What diffuser does is diffuser decreases the fluid velocity. Okay. Now let us go to turbine. Now let us go to turbine. So what will happen in turbine? What is the turbine basically? Turbines are work producing devices which in which what happens, that energy is transferred from moving fluid to the rotor. What happens, like if turbine has come here, then I will help you understand just quickly. What happens in the turbine is, this is not nozzle, I am trying to help you understand turbine. What happens here, some fluid comes into picture and it has got some what enthalpy with it, it has got some velocity with it. Then there is one rotor, let us say, installed at it. Then what will happen, that it will provide some impact to it, like it will try to what, put some force into it, then it starts getting rotated, and then this fluid will get discharged. Then what I can see about turbine is that it's a work producing devices which is exchanging energy by what? By reducing the enthalpy velocity of the incoming fluid and utilizing through what? Through an impeller on which rotor is mounted. Okay. Then again, when you will apply, let us say this is 1 and this is 2, then if you apply this steady flow energy equation to this device, then can you write down that again Q dot is plus m dot h1 plus v1 square by 2000 plus zz1 is equal to w dot plus m dot into h2 plus v2 square by 2000. This should also be divided by 1000 plus gz2 upon 1000. Then again what we will do, that we will eliminate those part. See, mostly turbines are insulated. Okay, like there is no heat loss. Like what happens, that if you are allowing heat loss, that means the irreversibility is anyway increasing. Okay, so heat loss we are not allowed. And what about the other changes? Potential energy change probably is negligible. Okay, then rest other things are considerable. Then they will ask you that, tell me what is the work done achieved from this turbine. Then can you write down, the work done will be nothing but m dot into h1 minus h2. Can I write down, plus can I write down m dot into v1 square, or let me take out 2000 outside, minus v2 square, plus can I write down, okay, we are done. Why? Because we have neglected the change in potential energy. So work done, I can see that this is the difference between enthalpy. So can I write down, this is delta H, and this is delta kinetic energy. Okay, so your W dot is this. Like, see, if sometimes they mention you these data, like this is not every time that they will say you that this is 0. Sometimes they mention this data, let us say that any particular value. Then what you will do is that you will not make them 0 unless they are hiding the data. Let us say that they are not mentioning that what is the heat exchange. Let us say that they are not mentioning you that what is the potential change. Then what you will do is that if they are not mentioning, then I will probably assume them 0 only. Okay. So there are other similar devices like compressor. So what we can apply this for compressor also. So compressor, in what happens in compressor, that air will, what happens inside a compressor is that some air will come into picture and this will get compressed, right? And then this goes out of this compressor. Then they will ask you that tell me what is the work done required to compress it. Then again what you will assume that if they are mentioning you, see, and now you will be must be thinking that this is the reputations here, let us move forward, we'll apply. So similarly, what will be the assumption in a compressor? Q is 0, delta kinetic energy is also assumed to 0, delta of potential energy is also assumed to 0. Then can I write down that directly uh, W required is nothing but delta H. W required is nothing but delta H. Why? Because if I write down this equation in terms of this one, then can I write down Q dot plus W. Then in terms of delta H and the notation, if I use the final minus initial, then I write down this one as delta E plus delta, not delta kinetic energy plus delta enthalpy. This E was not there. Delta kinetic energy, delta enthalpy plus delta potential energy. Those values which will be given, you consider them. And if those values which are not given there, then you try to find out if there is any missing data. And if you find out that no, there is no missing data, we were what they expected us to assume something, so then we will assume what is big deal into it. Okay, next thing. Next is throttling, very important, throttling. We have seen multiple times questions appear from the throttling. See, throttling is nothing but the flow through a very restricted area. What do I say about throttling? It's a flow through a narrow and restricted area. Okay. So flow through a narrow and restricted area is throttling. So what is the characteristic of throttling is H1 will be always H2. But this Q value, this is not equal to 0. And W value is always 0. So see, whenever they say that, okay, like they will say you that a certain substance is being throttled, then yeah, Q is also 0. Q is also 0. No, it's not like that the Q is equal to not equal to 0. Q is also 0. There is no heat interaction. If there will be heat interaction, then this will not be throttling, right? So in throttling process, Q is 0, W is 0. There is no delta KE. There is no delta PE. Then we are bound to achieve that H1 will be equal to H2. Then this is also called what? Isenthalpic. So there can be question in the exam, they will ask you that isenthalpic process is also called, then you need to remember that this was called throttling. And what is the very important characteristic of throttling is that it always, like let us say that you are throttling some wet substance like or some liquid, then what will happen is that the pressure will always decrease after throttling. Pressure will always decrease after throttling. Okay, this is one thing. And what is this process called? This process is irreversible adiabatic. Irreversible adiabatic. So mark these words. Irreversible adiabatic, and pressure is always decreasing. And the third most thing is that it changes the phase. Okay, when there will be liquid state now, then what will happen that if you throttle it, the liquid will change into liquid plus some amount of vapor. So these are few practical devices on which we will like we will see questions in the exam where they might ask you that tell me how to find the unknowns. Like they will ask you velocity, they will ask you heat transfer, and they might ask you what is work transfer and all. Okay, then there is one very interesting phenomenon which is called free expansion. Very important, very important, free expansion. What is free expansion? It is expansion against vacuum. So expansion against vacuum is called free expansion. Expansion against vacuum is called free expansion. So what does it mean? Like, see, whenever you are trying to expand some gas, then what will happen that the neighborhood gas molecules will try to oppose its vacuum, its expansion, right? Like in always, like expansion means what, that you have compressed something and now you are trying to make it free. Like if you compress some gas, like let us say that you are inflating a balloon, and then when you are not tying the nozzle of the balloon, then what happens that air is trying to come outside. So this is nothing but the air is trying to expand itself, right? Like whenever it is getting some space to occupy, this will try to occupy. So what is free expansion? When you are de-inflating the balloon, what happens is that there are air molecules in the atmosphere. So these air molecules try to restrict its expansion or try to hinder its expansion. Okay, so then there is one thing came into picture, that if is there any way that we can eliminate this restriction part, like the atmospheric molecules which are trying to restrict, can we eliminate that part? Then the answer is yes. Then it is only possible that if you have a vacuum chamber. If you have a vacuum chamber, since there is no molecules of air, then if you rupture it, this let us say that there was some gas here, some gas here, it has some pressure, temperature and volume, and then it was separated by a membrane, and there was another side where there is vacuum. And then when you puncture it, then what will happen, these gas molecules will try to occupy this vacuum space very very with very much speed and very quick, right? So these gas molecules, when try to occupy this vacuum, this is called free expansion. Why? Because this gas is expanding but there is no hindrance. Then I can say that yes, this is free expansion. And then can I say that in this free expansion process there is no work achieved. In fact, work done is zero, and this is insulated also. So Q is also 0. And what about delta H? We will find out what is H. We will find out. Heat and work is directly 0. What is delta KE? 0. What is delta PE? 0. Then you will find out that there is temperature initial. Why? Because your energy will remain constant. Why? Because everything, if it is constant, then there is no flow energy, there will be internal energy only, right? Why? Because there is no flow from outside. Now like here only the gas molecules which were at rest is taking the new position. Then I can say that U1 and then U2, but since this is an insulated molecule has gone nowhere, then I will say that U1 is equal to U2. And for gas, the U1 is function of temperature only. Then I would say that T1 is function of T2 only. So in free expansion process, I can say that the temperature at 1 is equal to temperature at 2, but there is no heat and work interaction. But particularly what you will do that you will say that in free expansion there is no work achieved. They will keep on asking you question that expansion against vacuum is called what. They will ask you that what is the final temperature. They will ask you that what is the work done achieved. But one very interesting phenomenon about it is what happens that molecules were at this position and then they have occupied this new position. Then can you see that the temperature initial is equal to final? But can you say that this process is isothermal? Then answer is wrong. This process is not isothermal. This process is not isothermal. This is not isothermal process. Why? Because even though the temperature initial and final is same, but meanwhile the temperature is continuously changing. Yeah. So that is why I say that the temperature, this is not an isothermal process, even though the initial and final temperatures are what? Same. Okay. Let us move to quickly one thing called unsteady expanse. Unsteady what? Flow. Like we have seen the case of steady flow. Now, this we have like a nozzle, um, turbine, compressor. These are nothing but steady flow devices. Why I'm telling these as steady flow devices? Because the mass flow rate, the enthalpy and other things are not dependent upon the time. Because once your system has started, then it will remain in that particular one working condition for a longer while. So that is why I name them steady flow energy devices. But there can be scenarios where your flow will not be steady. Then these are nothing but unsteady flow. Then let us try to understand unsteady flow. Unsteady flow means here your things are getting dependent upon mass. So what will happen that the properties are varying with respect to what? Time. And it may happen that you are changing even the mass flow rate, like same mass flow is not going out of the system. Let us say that if you have a control volume, like volume is anyway remaining constant, but what will happen, let us say this is the open system, then it might happen that you will be regulating the mass flow rate. Let us say that this mass flow rate is entering here and the mass flow rate is going outside here. Then this might happen that mass flow rate at entry is not equal to the mass flow rate at the outlet. This is also possible. So we can see that with respect to time, that there are so many things which have got dependent upon the time. So if I say that this is the mass flow rate at outlet and the mass flow rate at the inlet, then if these two are not equal to each other, then can I say that if I apply conservation of mass, if I apply conservation of mass, then then can I say that dm by dt, that is change in mass flow rate with respect to time, will be equal to what? Mass flow rate at entry minus mass flow rate at the outlet. Okay, and can I say that this is the amount of mass which is conserved, means which you have, see, if this is equal to this one, then there is no mass conservation, right? Then like all the mass is going outside. But if these two are not equal to each other, there is some difference existing between those two, then I will say that there is some mass which is conserved into the system. Okay, then I will apply the energy conservation equation. See, this is the step by step how do we apply this unsteady, like how do we analyze this unsteady flow. Okay, then we will apply energy conservation. Then when you go to apply energy conservation, then what you would write is that dE by dt, right? Like what if energy in is equal to energy out, then there is no differential existing. But if energy coming in is not equal to the energy going outside, that means again you have started conserving that energy. So can I write down that this will again be the difference between initial or the entry minus outlet? Okay. So can I write down this one as d upon dt into the mass flow rate at entry into what notation we have used is mi. So mass flow rate at the entry into enthalpy at the entry. And rather than writing it as rate, why? Because this is differential now, so this will take care. Plus kinetic energy at entry plus what? Potential energy at entry plus what? What is the rate of heat you are supplying? This is the what? This is the differential of what is entering into your system, and what is going out of the system is d upon dt. M mass at outlet means and into enthalpy at outlet plus kinetic energy at the outlet plus potential energy at the outlet and plus what? Work done. So this is the dE upon dt. So I know again now that energy conservation equation for unsteady flow. Okay. Then if there is certain approximation that there is no change in kinetic energy, kinetic energy, potential energy, then can I write down dE upon dt is equal to what things are left with us is d upon dt m I h I plus cube minus d upon dt m outlet h outlet plus w. See, now what happens in some special cases is that they will tell you what, like, uh, there is no heat, there is no mass going outside, there is no work achieved and all, any combination of this. So this is the generalized form and you can apply it to the any given scenario to you in the exam. So what are the applications? Like, let us apply this. We have seen now. So like, we have applied this, all the equations we have derived to, we have applied to some what special cases or general substances. So we will apply now this equation to any of the given case. So let us applying this equation for what? For for gas filling, or gas filling is also named as what? Charging, or you are trying to charge a evacuated chamber or even filled chamber. So let us say that I am applying this concept for one of the special case where your chamber is initially evacuated. This is the chamber which is initially evacuated, and this is a, let us say that, gas pipeline, and you are trying to charge it, and your mass is coming into it. Okay, and here you have some nozzle to regulate the flow. Then what happens that you have mass equation, conservation of mass equation, and conservation of energy. So let us first write down conservation of mass. So what is dm by dt is, what did we write dm by dt? Let us go to that. That we wrote it one as mass entering minus mass which is going outside. So can we see that if this is the chamber and no mass is allowed to go outside, then this will be, if the no mass, if no mass is go to allowed outside, then mass flow rate change will be the entering mass only. One thing. Second, why? Because m dot outlet is directly zero now, because there is no mass which is allowed to go outside of this system. And the second thing is dE upon dt. So dE upon dt, let us go to this reduced one. Okay. So if there is no mass in the initial one, like there is no mass in the initial one, then can you see that this term I'm applying here only, like dE upon dt is like if there is no mass in the, no, this term will become directly zero because there is no mass coming into the system, and this is also zero because there is no mass. So this term is directly neglected and this term is only remaining, and Q interaction is also zero only. So can I write down this one as d upon dt, mass which has entered into enthalpy which it has carried. And what about dE upon dt? This is nothing but the system only, right? And let us write down the dE of system and let us cancel out this dt dt. Then can I write, see, this is nothing but the mass flow rate only. Why? Because the hi is the constant. Then can I write down dE is, can I write down E2 minus E1? I can write, yeah, is equal to m dot h1. And can I write down mi, let us say better. So E2 minus E1, what is the energy of this chamber? Energy of this chamber, initially this is 0. And what is final? This is nothing but the stored into the internal energy, not enthalpy. Why? Because whatever has come into picture has got settled down. It is not flowing anywhere. That means it is constant. So this is U2 and E1 is directly 0. Initially this is evacuated and this is M entering into HI, and U2 is what? M dot CVT2. And what is this m dot? U2 is nothing but whatever is the total amount of mass entered. So can I write down that mi? Why? Because this is the amount of mass entered, and m dot I, and h is nothing but Cp into Ti. So can you see now that mi got cancelled? Then if someone asks me that what is the value of T2, then this is Cp upon Cv into Ti. So this is T2, which is the final temperature, is nothing but this is gamma. Cp upon Cv is gamma, gamma into Ti. So can I say that this T final in the filling is gamma times of Ti when the cylinder was initially evacuated, provided this is mentioned that this is initially what? Evacuated. Okay, so questions might appear, and they have appeared many times, that they will ask you that tell me what is the temperature, final temperature, if it is initially evacuated, it is being charged by some charge line and all. So we'll directly find out using this concept. Okay, so this is all about like first law, its application into various devices as well. So from the next class onwards, we will move to second law of thermodynamics. Okay, so till this class we have completed first law of thermodynamics and its various applications. So in the next class, while starting, we will do few questions based on again first law of thermodynamics, few questions from steady flow energy equations, and then when we are done with that, then we will move to whom? Second law of thermodynamics. Okay. So let us stop here for today, and then we will study second law of thermodynamics in the next class.